Weak interactions. There is no particular name for the stuff that produces weak forces, in the sense that electric charge produces electromagnetic forces and color produces strong forces. Some people call it weak charge. Whatever word you use, all quarks and all leptons carry it. Leptons have no color, so they do not participate in the strong interactions. Neutrinos have no charge, so they experience no electromagnetic forces, but all of them join in the weak interactions. There are two kinds of weak interactions: charged, mediated by the W's, and neutral, mediated by the Z. The theory is cleaner for leptons than it is for quarks. So let us begin with the leptons. Leptons. The fundamental charged vortex looks like this. A negative lepton, it could be electron, muon negative or tau negative, converts into the corresponding neutrino with emission of a W minus or absorption of a W plus. Lepton negative goes to lepton neutrino plus W negative. This implies, of course, that lepton positive goes to lepton antineutrino plus W positive, is also an allowed vortex. As always, we combine the primitive vortices together to generate more complicated reactions. For example, the process muon negative plus electron neutrino goes to electron plus muon neutrino would be represented by the diagram. Such a neutrino-muon scattering event would be hard to set up in the laboratory, but with a slight twist, essentially the same diagram describes the decay of the muon. Muon negative goes to electron plus muon neutrino plus electron antineutrino, which happens all the time. Technically, this is only the lowest order contribution to muon decay, but in weak interaction theory, one almost never needs to consider higher order corrections. The fundamental neutral vortex is, in this case, L can be any lepton, including neutrinos. The Z mediates such processes as neutrino-electron scattering. Muon neutrino plus electron goes to muon neutrino plus electron. Although charged weak processes were recognized from the start, beta decay itself is a charged process. The theoretical possibility of neutral weak processes was not appreciated until 1958. The Glashow-Winberg-Salem GWS model includes neutral weak processes as essential ingredients, and their existence was confirmed experimentally at CERN in 1973. The reason it took so long for neutral weak processes to be discovered is twofold. One, nobody was looking for them, and two, they tend to be masked by much stronger electromagnetic effects. For example, the Z can be exchanged between two electrons, but so can the photon. Presumably, there is a minute correction to Coulomb's law that attributable to the first diagram, but the photon-mediated process overwhelmingly dominates. Experiments at Desi in Hamburg studied the reaction electron plus positron goes to muon negative plus muon positive at very high energy and found unmistakable evidence of a contribution from the Z. But to observe a pure neutral weak interaction, one has to go to neutrino scattering, in which there is no competing electromagnetic mechanism, and neutrino experiments are notoriously difficult. Quarks. Notice that the leptonic weak vortices connect members of the same generation. Electron converts to electron neutrino with emission of W- or muon negative goes to muon negative, emitting a Z. But electron never goes to muon negative nor muon negative to electron neutrino. In this way, the theory enforces the conservation of electron number, muon number and tau number. It is tempting to suppose that the same rule applies to the quarks, so that the fundamental charged vortex is a quark with charge -1/3, which is to say D, S or B, converts into the corresponding quark with charge +2/3, U, C or T respectively, with the emission of a W-. The outgoing quark carries the same color as the ingoing one, but a different flavor. It's not that the W carries out the missing flavor. After all, the W must be capable of coupling two leptons, which have no flavor. Rather, flavor is simply not conserved in weak interactions, because quark flavor typically changes at a weak vortex, as quark color changes at a strong vortex. Weak interaction theory is sometimes called flavor dynamics. The far end of the W line can couple two leptons, a semi-leptonic process, or two other quarks, a purely hadronic process. The most important semi-leptonic process is undoubtedly down quark plus electron neutrino goes to up quark plus electron. Because of quark confinement, this process would never occur in nature as it stands. However, turned on its side and with the U bar and D bound together by the strong force, this diagram represents a possible decay of the pion. Pion negative goes to electron plus electron antineutrino. For reasons to be discussed later, the more common decay is actually pion negative goes to muon negative plus muon antineutrino, but the diagram is the same with electron replaced by muon. Moreover, essentially the same diagram accounts for the beta decay of the neutron. Neutron goes to proton plus electron antineutrino. Thus, apart from strong interaction contamination in the form of the spectator U and D quarks, the decay of the neutron is identical in structure to the decay of the muon and closely related to the decay of the pion. In the days before the quark model, these appeared to be three very different processes. Eliminating the electron-neutrino vortex in favor of a second quark vortex, we obtain a purely hadronic weak interaction. Delta 0 goes to proton plus pion negative. The delta 0 has the same quark content as the neutron, but this decay is not possible for neutrons because they are not heavy enough to make a proton and a pion. Actually, this particular decay also proceeds by the strong interaction. The weak mechanism is an immeasurably small contribution. We will see more realistic examples of non-leptonic weak interactions in a moment. The fundamental neutral vortex for leptons, lepton goes to lepton plus Z, leaves the lepton species unchanged. Again, it is natural to suppose that the same applies to the quarks. This leads to neutrino scattering processes such as muon neutrino plus proton goes to muon neutrino plus proton. Z exchange also makes a tiny contribution to the electron-proton force within an atom. As before, this contribution is masked by the dominant electromagnetic force, but it is detectable in certain carefully chosen atomic transitions. So far, it's all pretty simple. The quarks mimic the leptons as far as the weak interactions are concerned. The only difference is that because of the confining property of the strong force, there are generally spectator quarks present which go along for the ride. Sad to say, this picture is a little too simple. For as long as the fundamental quark vortex is allowed to operate only within each generation, we can never hope to account for strangeness changing weak interactions such as the decay of the lambda. Lambda goes to proton plus pion negative, or the omega minus. Omega minus goes to lambda plus kaon negative, which involved the conversion of a strange quark into an up quark. The solution to this dilemma was suggested by Cabibbo in 1963, applied to neutral processes by Glasgow, Iliopoulos and Mayani GIM in 1970 and extended to 3 generations by Kobayashi and Masukawa KM in 1973. The Cabibbo GIM-KM mechanism will be discussed more fully in chapter 10. The essential idea is that the quark generations are skewed for the purposes of weak interactions. Instead of UDCSTB, the weak force couples the pairs UD'(CS')TB', where D'S' and B' are linear combinations of the physical quarks ds and b. Matrix D'S'(B' equal matrix VUD, VCD, VTD, VUS, VCS, VTS, VUP, VCB, VTB multiplied by matrix DSB. If this 3x3 Kobayashi-Masukawa matrix were the unit matrix, then D'S' and B' would be the same as DS and B, and no cross-generational transitions could occur. Upness plus downness would be absolutely conserved, just as the electron number is. Strangeness plus charm would be conserved like muon number, and so would topness plus bottomness like tau number. But it's not the unit matrix, although it's pretty close. Experimentally, the magnitudes of the matrix elements are 0.9705 to 0.9770, 0.21 to 0.24, 0.20 to 0.024, 0.21 to 0.24, 0.971 to 0.973, 0.036 to 0.069, 0.2 to 0.014, 0.036 to 0.070, 0.997 to 0.999. VUD measures the coupling of U to D, VUS the coupling of U to S, and so on. The fact that the latter is non-zero is what permits strangeness changing processes such as the decay of the lambda and the omega minus to occur. We can electromagnetic couplings of W and Z. There are also direct couplings of W and Z to one another in GWS theory, just as there are direct gluon-gluon couplings in QCD. Moreover, because the W is charged, it couples to the photon. Although these interactions are critical for the internal consistency of the theory, as we shall see in chapter 11, they are of limited practical importance at this point in time. See problem 2.6.